Welcome everybody to our latest in our monthly series of SLCan webinars. Today we're very pleased to have Anna Coppinger here from Architecture 49. She's going to talk about sustainable laboratory principles, do less with less, and get more. Just to give you a little background on Anna, she's an architectural designer at Architecture 49 with a deep understanding of planning principles for a wide variety of laboratory topologies. Anna works hands-on with the laboratory representatives to assess scientific workflows and processes and excels in developing planning solutions which optimize the use of space and equipment. She has a wealth of experience in design, detailing, and construction phase services. As a speaker on lab planning at numerous conferences in Canada and the USA, Anna's capabilities in lab planning have been recognized. Recently, she's been invited by the Canadian government to assist in the development of comprehensive lab planning standards for use by the 9 federal research departments. So without further ado, I will just take another minute. If you have any questions throughout the presentation, I just ask that you key them in the questions section there on the webinar, and we will certainly review them all at the end. Without further ado, I will turn it over to Anna. Welcome, Anna.
Thank you, Martin, and thank you everybody for signing in today. I'm excited to give this presentation to you. It's actually probably 10 to 15 years of developing ideas about how we optimize and design laboratories sustainably based on some earlier experiences that we had doing projects in developing and emerging economies. From that, we basically started to develop a core competency of thinking relative to laboratory design in North America, and we coined the do less with less and get more. The expression has teeth. It's really an indispensable framework for thinking when developing containment laboratory projects, especially in emerging economies such as Mexico and India. While the presentation sheet here says India, I'm going to focus a little bit more on Mexico. There was just too much material to go through, so I had to edit a little bit of this thinking and presentation and focus a bit more on the Mexico work that sort of led to the thinking, and then how we've sort of brought it home into our own types of thinking. The gentleman riding the bicycle in this photo is a client of ours, or was a client for a project at Tecamac campus, which was an animal laboratory that we were designing there. And at the startup meeting for this project, we were discussing all the complexities that, of course, we're familiar with engineered systems, stringent health and safety requirements, flexibility and adaptability issues, intensive energy use, environmental impacts, yada, yada, yada. And this particular gentleman was listening quite attentively and then asked me in Spanish, so this is a translation, he said, do I have to use treated water to wash down the animal rooms and the feces that are in there? And why do I need a second HEPA filter? Doesn't the first one work? And, you know, it really sort of sparked something in me when I was having this conversation, and it ended up being quite a long conversation after that. Because out of context, these questions might not resonate as major hurdles, but when you factor the fact that the campus on which the facility was going to be constructed had no municipal water or waste systems, that they relied on well water and a septic field infrastructure to support 8 major installations, and that at any given day they experienced multiple power outages due to unreliable utilities. The do less with less get more is really a lifeline for these types of clients in these places. So what sort of started all this? Mexico, Canada, and the US have an agreement, or a triad agreement, for dealing with infectious disease. We have no borders between our countries, and infectious diseases don't respect borders. You know, events such as SARS and H1N1 had really sharpened the collective awareness that humans and animals and the viruses they carry move around the planet at biological warp speed. and one constant is that economically we're not equal where these viruses are landing. So how do we ensure that all the nations are able to build and operate containment facilities without sacrificing biosecurity? How, in an instance of an emergency response that touches all three countries, can we send resources from Canada and the States to Mexico and vice versa, and people be able to work in environments that have the assured containment principles that we're trying to develop? There is, right the wrong way. There is an interesting statistic that the heightened mobility of disease has increased the demand for surveillance, storage, and diagnostic of research and dangerous pathogens. The biocontainment labs support initiative strategies and standards that safeguard public health against infectious disease threats. So this is a map that was detailed how viruses jump from different countries via the plane. A Canadian researcher, Dr. Khan, and his colleagues designed a system based on air travel patterns to predict how infectious disease will spread around the world. And for the H1N1 pandemic, the findings showed that the international destinations of travelers leaving Mexico in particular, including cities in the US and Canada, were strongly associated with confirmed importations of viruses around the world. So we understand that if strategies aren't found to ensure minimal building and operating costs are met, necessary projects in first world and developing countries may not be built and remain underutilized or completely unused due to the lack of operating funds. So the interesting statistic about our work going into Mexico was that we were initially hired to get some CL3 facilities up and running that couldn't be certified. So they had been built with minimal understanding about what the requirements were, and then they were trying to certify them using a Public Health Agency of Canada, or BMBL, which is the American equivalent of biosafety standards, in order to certify these facilities, and they couldn't. And so our work actually started with projects that were at many laboratory facilities and hospital facilities, mostly for HIV, trying to get them up and running as level 3 facilities. So when we started working, we started realizing that the context we were working in, we could not just transport all our understanding of what we do here directly there. We had to learn from what was happening in these countries and then see how that would change our thinking of how we design laboratories in our countries. So anywhere you design a facility, the primary objective is human environmental safety. This is non-negotiable. So how do we begin finding these creative solutions to minimize the operating costs in these countries when you're designing in places like this? This was a project we did in Chiapas, Mexico. Chiapas is down near the Guatemalan border, and it was an animal health level 3 ag facility for the Animal Research Health Association called SLCan in Mexico. And the site we inherited was a site that had been decommissioned. It was originally owned by Comexa, which was an American-Mexican partnership for the eradication of the screwworm, and that's only incidental information, but they had this entire building infrastructure that had been designed in around 1974 as a sustainable campus. You can see in the background of the photo there's 3 ponds. So the entire facility drew water from the river that you see there, Rio Grivial, I can't even pronounce it, Griava, and they would draw water up to a cistern. They'd gravity feed it to all their buildings. They'd centrifuge and separate solid waste from liquid waste. They treat the liquid waste in the ponds. I'm giving a very quick overview. And then they dump the water back in the river cleaner than it had been pulled out. And we had to design a level 3 ag facility to use this infrastructure here. It was a very interesting process. I don't have time to go through all the details, but one of the things that came forward was we really had to learn how to think about sustainability and the human element, key the conference that's coming up in October, which is how do people fit into the equation of sustainability? What does a building have to do, and what can people do, and what does the building have to do? So here's just some pictures for the type of, just to give you a sense of sort of the type of geography and infrastructures that we're dealing with. And all these locations, there was about 8 of them in our history of working there. They all had the same issues: unreliable power, non-municipal water systems. And so what is it that we were going to do? And we were able to design a lot of these facilities. I'm going quickly through some of these pictures just to get to the key points. So we were able to present and do drawings thinking about sustainability and what we coined as no tech, low tech, and some tech. So what this is really, we all know what this is because we've all been dealing with sustainable architecture and energy and how the vast environmental strategies that are out there, which are actually quite simple to explore and implement. There is the vast body of knowledge of how to design passively that minimizes engineered solutions through appropriate building orientation, material selection, harvesting of natural resources, etc. In the Heating, Cooling, and Lighting book, Sustainable Design Methods for Architects, Norbert Lechner outlines 3-tier approach to the design of sustainable buildings for heating, cooling, and lighting. The sustainable development industry, all of us on the line today and in our own practice, understand the value of this tiered approach. What we don't understand is that the no-tech and low-tech represents about 80% of the total energy reduction that we can achieve for any building type. And often there's this residual 20% that is a bit of technology that's going to offset what we couldn't achieve using passive and or other technologies for reducing energy and heating in a building. The problem in these emerging responses is that that bit of 20% is more of a chunk for these clients in these emerging economies that's associated generally with redundancy and fail-safes that we incorporate into our buildings in North America, responding to sort of increased risk assessments that we place on our projects and our facilities here. This last chunk of technology is really the crucial differentiator between the first and developing countries. The dollar amount increases substantially relative to the whole for the lack of and inaccessibility of twos and all the things that I've discussed previously. Without that, this technology becomes almost impossible to incorporate. So what then? What do we do? This is one of my favorite slides for anybody who is an animation fan. It's from the movie WALL-E. And if anybody's seen it, this is where they live in a world where the human has been released of any responsibility to do anything and relies on being moved around by all these robotic systems, and you can see they get a little unhealthy. But the point is we have to rethink the role of people in these environments. And if we respond to a people-first philosophy of work, we can explore various strategies that shift the operational balance in favor of protocols that are people-centered as opposed to building systems that are technology-centered. These strategies that we implement include, and I'll go through them in a little bit, protocol mapping and lean programming based on science, risk, and procedures. So from all this experience in Mexico and in India and other third world countries, we really started to roll in this programming and planning core competency of really thinking about breaking down all processes and not jumping to engineered or technical solutions or even providing the redundancies that we do. Let's understand your science, know your resources, and build what you need. And that applies whether you're in an emergency economy or you're in our economies. You have to know the risk. Understanding your science is about knowing the risk level. Are you CL2? Are you CL3? Are you CL4? containment level 3, containment level 4, for those that don't know the acronym. Know your resources. What geography are you building in? What money resources do you have? What people resources do you have? And the big one is optimize your building. A lot of the difficulties we had going back to when we first started working in Mexico was that they would build entire buildings at a CL3 level when really what they needed was a small suite at CL2 with some support at CL2+, and then some traditional laboratory work. So you really had to go through the processes. What was the science? What was the activity that you were doing? What needed containment? What were the risks of that work? Were you diagnostic or research? And then really building a program with the clients to then overlay the building infrastructure and find out what the building could do to support all the other protocols that we happen to be working with. And it all came down to that people were the IT resource that all countries share regardless of economic limitations. So this is what we talked about protocol mapping, and there's a lot of thinking that goes into this, but really what this was doing is we started to think about every science and every activity at every risk level at every time of day for a variety of different science functions and annotate exactly what people do in that system, how many times they're donning and doffing PPE, how many times that's going to instigate either a decontamination or a washing of equipment, of clothing and or equipment. And by mapping these processes in a very detailed way, we were able to start to minimize. What if people did this instead of this? What if we didn't introduce an additional doffing here? What would be the risk? But that would minimize the amount of supplies, consumables, washing, materials, everything that would be associated with the activity that slowly starts to build cost and starts to build infrastructure that you may not need if the science didn't demand it. So this is a sort of a global look at, it's excuse that it's partly in Spanish, but essentially what it's showing you is from the least containment to the most containment, and then to your support functions, what are the variety of activities that are happening that people are interfacing with, and what can they do, and what can the building do? So from that, we move forward and we take areas of buildings and we show them exactly what the areas that are involved in those processes, what rooms we need for each of these activities and assumptions, and slowly we start to optimize the program to a more lean and optimal flow and process that is heavily people-centered versus building-centered. So bringing it home, we had to figure out how were we going to take all this years of thinking relative to working in countries that didn't have the resources that we had here, but apply the principles for it. And we know that ultimately, any laboratory is going to be about program flexibility, operational flexibility, the protocols in the buildings, how the systems integrate, your life cycle cost choices, and of course, how sustainability impacts all of that. With that, we started thinking, well, what's the fundamental question that any facility owner or stakeholder is going to ask if they are in Mexico, in India, in Canada, or in the USA? What drives the needs of the laboratory, and how are these needs going to be defined, and what are the costs to meet them, and how can we roll in all this experience in these countries to create a very lean and optimal framework or core competency for programming and planning these laboratories? I don't expect you to read this slide, but this led to a framework of understanding that talked about need, which responds to a question is what's important to me being the stakeholder of a facility. The challenge is how is the industry, whether it's the scientific industry or the building industry, understanding the needs that have been defined. what are the solutions, what are the strategies for how I need to achieve this, and what is the analytical process to do this. And so this started forming a whole framework of thinking that is applied to how we structure laboratories and how we start to program with the client their scientific needs that ultimately lead to physical spaces. So what is important to me? We did a little bit of research regarding sort of what the typical scientist or lab user in a facility that to be important for them. This is a list of a whole bunch of issues that came out on top. This was a survey done by R&D Lab magazine. And it talked about cost efficiency of construction, of operations, functionality, energy efficiency, and you go down the list, and then there was sustainability features, was this small line that was part of a large list of things that were considered to be important in labs. And this was the result of the percentages of what is important to me. And you'll see that out of this, all these percentages, they're going to, you know, functionality 70%, cost efficiency 68%. When we went down to sustainability, it was only 33% important to the general users. And I think a lot of it had to do with understanding that they didn't have an understanding of exactly what that sustainability is, or how the human element or the person as the it resource can really impact sustainability initiatives and patterns. And so ultimately, it was determined that in this particular study that labs tend to shy away from green building because they think it's going to be expensive. But if they didn't have any budget constraints, they would place it at a higher priority than they have with their budget constraints. And the aspiration is being open-minded and experimental regarding new technologies. And so we've highlighted that because it's not necessarily new technologies that we have to consider. We have to consider how we plan and impact things, not considering technology first. So it ultimately, going back to understanding your science and knowing your resources and building what you need, it really places the utmost importance on the planning and operational concepts and pre-design and early pre-planning for all these facilities that will ultimately provide the most value to your stakeholders. So finding the right balance of what we call alterability, and this becomes important because we talk about, sorry, here it is, I missed one. Alterability is a concept that embraces flexibility, adaptability, and scalability. So we talk a lot about alterability, and we had to find a word that embraced sort of all the concepts, because in a laboratory, when you're talking about planning and optimizing space and having multi-purpose and easily convertible spaces, you're talking about flexible. And really that's at the user level, and it's at the bench level, and it talks about a flexibility that can be obtained without using infrastructure staff, without having additional monies for renovation, etc. Adaptability is a bit more of a long-term concept, and it has more impact on permanent infrastructure. It would say, for example, in your fume hood manifold system, you might allow for some additional connections for future fume hoods, or similarly for biosafety cabinets if it's a B2 cabinet. And scalability really has to do with, you know, are we allowing for, in our planning, expansion of a new addition? Are we allowing for an expansion of additional floor? So can the project be scaled up or scaled down easily? But adaptability and scalability tend to have more infrastructure costs and renovation costs than do flexibility concepts, which is at the bench level. That's how we've sort of tried to break apart some of that thinking. And so when we go back to how we apply the whole notion of sustainable design, how we apply organizational concepts on the site and planning concepts in the building. This is a small diagram that's trying to talk to the concept of the low-tech, no-tech, some-tech pyramid. The concept of a program, this is an example program that is saying most laboratories have their minimal program is on the non-containment side, and the maximum amount of program is generally on the containment side. And this is the part that's going to give you the most grief when it comes to budget and cost. So we really have to understand how we can best optimize the orientation of a building on the site and all the low-tech, no-tech strategies in order to minimize any kind of additional engineered systems that might be required for that 70% of the building versus the 30% of the building. And how we do that is generally by how we locate a building on a site, by placing labs on a north side, by placing offices on the south side, by optimizing an east-west orientation, by stacking things to minimize distribution and zone your expensive HVAC and or exhaust systems. And so there's a lot of strategies associated with the planning and optimizing of the program that then leads into plans and optimization of the building on the site. I just wanted to show you a little example about the alterability and lab modules. If we dive from the big and dive right back in, which is a lot of what we do when we're working on these projects, is we're looking at the minutia, and then we're looking at fast forwarding to the impact of how that aggregates and what that means for the building, and then coming back and tweaking the actual module to make sure that the planning increment or the DNA of the building isn't flawed or contaminated, and when we blow it up into a 40,000 square foot footprint, it's not going to lead to a series of additional errors or fundamental flaws that'll be translated and create major problems in the entire facility. So we often talk about alterability relative to open, enclosed, and dedicated labs. We have modules that have multiple uses, whether they're instrument rooms or wet or dry bench labs, but the module itself has a capability to be used as a multiple types of science function. But the key here is that when you go to an open laboratory module, which means no walls, a series of benches, you're assigning activities and equipment to different groups in the laboratory based on their need, but you're not isolating because the science doesn't necessarily require the isolation. Obviously, if you require isolation, you're going to be in an enclosed and or dedicated lab, but really we understand as designers that this is where you begin because it has the maximum amount of alterability with the minimum service load intensity. And as you start to enclose labs and you start to become more customized and you start to become completely customized, your flexibility is going to become minimized and your service load intensity is more than likely going to increase. So when we start thinking about the science, know your science, is there a risk to a bunch of people working in the same places? Can protocols manage how people use individual bays and shared pieces of equipment in an open lab environment without risk of contamination of the product and or safety risks to the person? And so we start here, and only where absolutely defined and needed through that protocol mapping, through an understanding of the process, do we start to introduce the enclosed and then finally the dedicated laboratories. Martin, how am I doing for time?
You're doing fine. Just you're about a half hour in now.
Okay, perfect. So there's some slides I'm just skipping over because they really are detailed slides about how you take that module and you convert the need based on the program and the science, but coming up with something that has the most optimization for the most types of programs is what the goal is, and then how people use that and what protocols they're using will determine whether it's open, closed, or dedicated. We then vertically aggregate, so the little module that we were talking about is a tiny little box in here, and we figure out how we can lay out all these increments of modules based on the program in a zoned and organized fashion that groups support functions or these enclosed and dedicated labs with your open labs, with your office spaces, and you create a very distinct and optimal zoning for your systems infrastructure. The goal being always to isolate any kind of heavy infrastructure in enclosed areas together and allow your open laboratory area to be as flexible and unencumbered by fixed things such as sinks and plumbing elements and fume hoods as possible. Different science programs will hybrid this base model that we always start with, and it'll start to change and vary based again on the science need. But generally, we've been able to go back to this very basic and simple organization of a laboratory in terms of zoning of modules and zoning of science, and then slowly bring that up to something that might have more load intensity if it's required. And then actually that was the end of my presentation. I wanted to leave lots of time for questions because I threw a lot at you.
Okay, thank you, Anna. Very interesting to see how you've integrated all those various things. It sounds like it was a lot of work.
Well, it's an ongoing process, and it certainly isn't done yet. But it certainly gave us a real sense of what our core competency had to evolve and develop to, because at some point we're all going to be in a position where resources are a challenge, where we don't have necessarily reliable power, and if we continue on in the path that we are, using the infrastructures that we do and the redundancies that we incorporate into these facilities, I think ultimately we won't be in a very different situation. So we need to start thinking about these in all our facilities that we work on now.
And how have you found the acceptance out there in the marketplace with this kind of thinking?
I think it's been generally very positive. You know, when we're starting on a new project, we don't necessarily tend to give the whole background and how, you know, all this thinking developed, but we do talk about know your science, understand your resources, and build what you need. And I think industry and science and stakeholders, everybody can appreciate that you really want to understand what it is you're doing, how you're doing it, what money I have, what people I have, and what do I really need to build. And that is universal, and it is, you know, I think very well accepted by the majority of clients that we have an opportunity to work with.
Mm-hmm. Well, that's interesting. Okay, well, at this point, I don't think there are any other questions. If anyone's out there and has a question, please submit it now. And I think we just got one here.
Do I see these questions, or do you read them, Martin?
I'll read them out to you. One sec here. I'm not sure why it's giving me a hard time to look at them, but hi, Anna. Could you expand a bit about passive systems you implemented in the Mexico facility? Not sure I understood all the solutions that were implemented.
Yeah, absolutely. So here, let me go back to, which one can I go to? So in this Chiapas project, one of the important factors, and we were using existing infrastructure, one of the important things was to orient the building relative to the site. Chiapas is quite low and the sun is quite high, and it was interesting. I don't have the slide here. We did a lot of solar studies to understand how the shape of the building, which ended up looking like this, how the shape of the building, looking like this, could impact heat gain. So it was very interesting because of the angle of the sun. Same principles. We situated the labs on the north side, the administrative and functions that didn't really need to have the same tolerance or control as the laboratories on the south side. Those areas were passively ventilated. So anywhere that we could passively ventilate, we did. So you had low draw underneath in the windows, and we had high level exhaust through louvers and skylights above that were operable and opening manual, not electronic. So all the areas that were not considered containment areas were designed passively. All the water systems were integrated with the gravity-fed system, the large cistern that was on the top of the hill. So all the water was gravity-fed to our building. All the water was treated initially from the containment areas, but then the treated water was moved through the ponds. It was treated to a different level and moved through the 3 different treatment ponds, which have different types of plants and species that would take out the balance of any contaminants that were in there that were non-biological contaminants. Obviously, those had been already dealt with the systems, and then put it back in the river with the rest of the water off of the site. With the shape of the building, it was interesting. It was small moves of angling facades, slightly northeast or slightly southeast, that would really reduce the amount of heat gain, especially in the CL2 and CL3 areas of the laboratories. And so the building shape, orientation, percent of windows was all to do with solar studies that we did in order to optimize those systems. The strategies for load reduction was we really considered redundancy as a extra in terms of systems, and the redundant principles for certain things were all people as opposed to building systems. So we didn't have dual emergency generators. We didn't have, I'm trying to think now, I'm at a loss for all the different mechanical systems that were there. But redundancy was minimized significantly because they just didn't have the resources, A, to purchase them, and B, to maintain them. So we relied a lot on protocols that started with the people to minimize how much energy you would use and how much backup you would need in the event that something failed. There was always a people protocol to continue doing the work.
Okay, we have another question here. How essential is facility maintenance and operations in the long-term success?
It is absolutely critical and necessary. You have to have a long-term operation and maintenance plans for your facility. And if you design a building that you can't afford to or staff to maintain, it's best not to even start to build it. So you can't ignore that part of the programming and planning and decision making. You have to always jump to, if I install this, how am I going to operate it? Who's going to operate? Who's going to maintain it? And then move back and make determinations about what that system actually is in order that you can. Going back to the start of my presentation, the projects in Mexico were exactly that. They either couldn't meet certification or they couldn't operate them because the systems were too complicated. The parts were foreign. They didn't have servicing contracts or agreements. And so they couldn't do the work that they needed to do or the science that needed to be done because they didn't have that long-term operating and maintenance plan in place for the decisions that they made in the beginning when they built the facility.
Very interesting. Thank you. Well, Anna, that's all the questions that we have right now. So on behalf of SLCan, I'd like to just say thank you very much. It was an excellent presentation.
Well, thank you. I'm really passionate about the stuff and I enjoy talking a lot about it. If anybody is interested, there is an article that was published in the Anthology of Biosafety, 14th edition, called Sustainability, and the thinking or the article around do less with less, get more is published in full there. I could certainly send Martin the link to what that is, and if anybody's interested, that they can go online and read all the juicy bits that I probably left out in this presentation.
Okay. Well, thanks again.
Okay, you're welcome. Thank you.
Okay. Okay, bye for now, everyone.